Thank you very much, everyone, for being here, the audience for showing the interest in this workshop, the authors of the contributed papers for sending their work, which I think all of them align very well with this spirit of this workshop about closing the academia to real-world gap in service robotics. And of course, I would also like to thank the panelists for accepting this invitation and also for sending their contributing material. So let me just quickly introduce the organizers. So we are organizing this together with the University of Washington and Imperial College London and Preferred Networks, which is the company I'm working for. So the first, let me unshare this. So Nick Walker is from the University of Washington. Are you there, Nick? Yes, Nick's there. The other organizer is Maru Cabrera from the University of Washington also. I don't know, is Maru here? Maru, maybe not yet. Maybe not yet, okay. And then Peter Kormushev.
Yes, hello everyone.
Imperial College London. Yes, and myself. My name is Guilherme and from Preferred Networks. So the way this workshop, we try to organize this workshop is to have basically 3 sessions. So the first, well, the first part is these opening remarks. That's exactly what I'm doing now. Then we'll have a first session, which will be about the contributed papers. So this will take like 30 minutes and Nick will chair this session. And then the second session is about the panel, which will last 80 minutes. And that's where we'll have, the discussions with the panel. And then we'll have a third session, which about, free discussions. This is optional. People who want to leave after the second session, they are okay to leave. But, people who want to stay a bit more and, talk about any other topics, feel free to do so. So just to give a bit more of context before we dive into the talks, I just want to, basically just give some what I consider as the gap that we see in terms of academia and the real world. And I think one of the ways to see this gap is in terms of the technology readiness level. So of course, in academia, we are interested in these TRLs that are very low. I mean, we basically start these technology levels, right, in academia with the basic scientific research. But in the industry, of course, our interest is much higher. We want to deploy robots or we want to provide a service or some commercial product. So this TRL usually, we need this to bring these TRL levels much higher. This is one way of seeing the gap. I think another way where we can illustrate this gap is basically by the metrics that we care about, right? In academia, people care about publications, the grant, the funding for the lab, students care about graduation, professors about tenure and everything and all this stuff. But I think everything boils down to, we want to publish good scientific papers. But of course, the metrics for industry, I think, although we always see some very nice motivation or vision for companies, it doesn't matter what is the greater good that we want to achieve as a company, everything in the end boils down to, can we make money out of that or not? So I think, it has to be profitable. So very different metrics here. Another way of seeing this gap is in terms of assumptions that we make. You see this picture here. Let's imagine like a robot that has to do carpentry or work as a collaborator for some carpenter. The real world is basically we cannot make assumptions in the real world, while in a lab, and this is a picture that I took from my own paper, so I can basically slam myself on this. We make a lot of assumptions in the research, right? We don't even talk about them. I think that's another problem that I would like to discuss in this workshop. There are so many things that are behind the scenes, occlusions and, you know, how the way we prepare all these experiments. And even when we try to sell this as a system that work with naive users, even this naive is already kind of fishy because it's not really naive, right? It's usually some other student that's also used to do robotics. And another way, which is something that's a bit more recent in my experience, is the way how things are done. Like in academia, it's usually this long endeavor, like one-man work, where you are basically, I don't know, you're a PhD student or some postdoc, and you have many years to try to really dig deep into some fundamental problem. And it takes a lot of time. But in the industry, if you go to some company, you see it's many men work, like many people work in the same problem. And we don't talk about years, but we talk about months. So the way things are done, you know, to bring this, basically to elevate this TRL, this technological readiness level, it's very different, I would say. And of course, I think there are many other ways which we could illustrate what this gap is. And I think the general, let's say, consensus is that it's better if we can decrease this gap. I think there are many reasons that this would be good. We would have faster, you know, technological transfer, more research funding being translated into useful products and services, research with the more realistic and practical outcomes, metrics and policies that align academic and industrial interests, more support and collaboration between academia and industry, it's also always good. And I think this is something that always happened, like this growth and support of researchers in industry. I think there was always this flow of people in academia going to industry, but especially now with all these startups in robotics and AI that we see nowadays, this is getting even maybe bigger now. So now that we have this critical mass being shared in both camps, academia and industry, I think it's a good time to talk about this gap. So just a bit before we start really these discussions, a bit of how to interact now that everything is online. The panelists and the authors of the contributed papers, please feel free to unmute and speak whenever you want. And also keep your video on so we can see you. For the general audience, I would ask you to please keep your camera off unless you are making a question. Sorry if I turn you off at some point because you want to really separate like the audience from the panel. I think it's better. But you know, you can interact with the panel and with the authors by writing your question on the Zoom chat, or if you are doing this from the portal of RSS using the session, you have also in this feed loop chat for the session of the workshop. You can also make questions there, and we'll be looking at that. And of course, I suggest you, if you also to raise your hand and wait to be unmuted, and then you can make the question yourself, which I think is more interesting, more interactive. And if you don't know how to use that in the Zoom, actually you'll see that there is an icon there with these participants. If you click this icon, you'll see that the panel on the right will open, and then you have the option there. You should see this option to raise a hand. So if you want to make your question, please feel free to use this option also. And yeah, before everything else, this session is being recorded. It's actually already being streamed live to YouTube. And after this finishes, it will be hosted in YouTube. So yeah, I just wanted to make this clear. If you have any problem with that, please let me know. And so with that, we can start this first session with contributed papers, and I will actually let Nick take over from now. So Nick, please, if you can share this session.
Sure. Okay. So can everybody see these slides?
Yes.
Great. So we've asked the authors to send us some pre-recorded video presentations, which we'll play, and then we'll have 3 minutes for questions afterwards. So beginning with perceiving signs for navigation guidance.
We don't hear the audio.
Oh yes,
Ooh.
there's no audio.
1 second. Let's fix that. Share computers. All right. Let's try that again.
I'm Yin from Cornell University. I'm Yin from Cornell. I'm Yin from Cornell University. I'm Yin from Cornell University. Today, Lassie and I are going to present our work, Pursuing Science for Navigation Guidance in Spaces Designed for Humans, which is supported by Professor Hariharan and Professor Chris Gazit. Claire and Chen will be answering the live questions afterwards. So what are human-made spaces? Human-made spaces are spaces that are designed to make navigation easy for humans, such as malls, airports, and stadiums. Traditional motion planning often depends on an assumed perfect map as input. The robot takes a perfect map and a goal, does motion planning to compute safe trajectories, and then follows the trajectory as closely as possible. However, a perfect map is expensive and not applicable for all robots. Reliance on perfect maps can result in awkward interactions. For example, the state-of-the-art guide robot in Incheon Airport sometimes spins in a circle as it tries to orient itself, not using the context clues from its environment to navigate. But what if, instead of relying on a perfect map, we use the same cues, which are the signs that humans use to navigate? Prior work shows that science can generate a complete global plan. Assuming perfect sensing, aka given a fixed sensing radius, the robot has full knowledge of obstacles and signs in the scene. In this work, we seek to emulate the prior work's perfect sensing abstraction using 360 image input.
So a human-readable sign is characterized typically by the sign's text and directional arrows associated with the text. The other important characteristic of the signs is the grouping of the text with the arrows. However, we need to be mindful of our predictions because the arrows might be on varying sides and the text could be in different fonts, styles, and sizes, or even as subtitles of non-English text. For sign perception, we have developed a proof-of-concept vision system which takes in still images of various sizes collected from Google Street View and from cell phone camera photos as part of our airport dataset and outputs a sign characterization. The vision system has three major components. The first is a text spotter that identifies the sign text. This works alongside an arrow detector that localizes and estimates the orientation of arrows. The last stage groups the sign text with its corresponding arrow and outputs the result. The text spotter is implemented based on a current state-of-the-art text spotter, CharNet. The arrow detector is implemented by first fine-tuning a pre-trained mask RCNN model in order to localize relevant arrows in an image. Then, a template matching approach is used to estimate the arrow tip within that localization. The arrow's orientation is then computed as the angle between the vector connecting the arrowhead and the horizontal axis of the image patch. The grouping is determined through a nearest centroid computation between the arrow and text bounding boxes. This photo describes an ideal success case of the vision system. All text of interest is identified correctly, along with the arrow in the image. The arrow's angle is accurate, and each instance of text is correctly grouped to it. We'd love for all predictions to be like this, but there are several potential failure modes. For example, the arrivals text detection in this image is missed altogether, although the toilets are identified correctly. In this photo, which just shows the arrow predictions, both of the arrows are identified, but the angle predictions of the leftmost arrow are very incorrect. When text and arrow detections are missed, a common failure example is an incorrect text arrow grouping like the one shown here. Our ongoing challenge is to incorporate our branches into a single end-to-end model in order to streamline the computations and potentially allow for faster, near real-time sign characterization.
We simulated navigation in 3 airports, LYS, MDE, and MPL. Compared to a random walk-style baseline, science created a 23% improvement in the trajectory length in the LYS airport, a 5% improvement in the MDE airport, and a 17% improvement in the MPL airport. We intend to run this on 2 real robots. One is the Vector. It's a small robot to run in artificial environments. And for a final trial, we have the BIM, a human-sized office telepresence robot, augmented with a 360 camera, meant to be run in a real mall or a real airport. Thanks for listening.
Great. Do we have the authors here?
Yeah. Hi,
Yes.
can you hear me?
Yes. So again, if people want to type questions in the chat, feel free to, or if you want to unmute and ask directly. But I'll open with one. So the idea of using a single model for detecting these signs and these arrows, you know, a combined model sounds great, but it seems like it'd be a hard data problem. So can you talk about ideas you have as far as getting data that would be necessary for training something like that?
Yeah. Cheng, do you want to answer this question if you're here?
Sure.
There's two of
You
us.
guys hear me?
Yeah, I can hear you. You want to turn on video?
My video is on, actually.
Oh, cool. I see you.
Okay. So we have already collected a data set that we use to fine-tune the Mars RCNN. So we have data set. The data set is a combination of Google Street View and some images we took using cell phone. So we can always use those to actually train a model. As for collecting enough data, there are a lot of ways to reduce dependency on annotation. One thing is to use a pre-trained model. So usually a visual recognition model consists of two components. One is a feature extractor. One is a model-specific learnable component. The feature extractor are usually very generic. What it does is map images to a vector. You can always use a feature extractor that's trained on other data set for other tasks, and then use it on whatever task you want to do. So we are thinking of using maybe a feature extractor from Mars RCNN, just change the task-specific component for our problem. And that way we can reduce the amount of annotation we need. Does that answer your question?
Great.
So there's a question in the group chat. So Claire, do you want to answer that?
Yeah, should I answer the ones in the group chat, or is there like an ordering for this?
Let me read it out so it gets archived. So how does motion or path choice help? Given a motivation is to make motion planning more robust, is it possible to pick different routes to make the grouping better?
For the grouping, by group, does it mean grouping of signs to current path? I'm not super clear on what that means.
So I'm the one who asked the question. So in your examples you show, it seems to be that your network is processing them on still images. And does your network, or do you see can you comment on what would happen if you were actually to allow the network to change the path taken when it sees some errors?
Yeah.
Your motivation in the beginning was to make motion planning more robust, right? So I'm saying motion planning might be also able to help you they can work together. So they might be able to help you get better information from the science. So for example, maybe when you showed the example with the toilet and the arrow, maybe if it had just turned the robot a little bit, it would have been able to figure that out.
Yeah, so that's a really big part of our next steps, actually integrating with the real robot, because then you can make it an active problem and actually take motion into account when you're just doing the detection.
Yes, exactly.
We're not going to do it. So it's just like we're live streaming in image input, and we're constantly just running the model frame after frame, because that's inefficient and not really feasible. So it is like definitely part of our next steps. Like the way that we do planning right now assumes like it doesn't assume a map. Something I think we didn't emphasize in the presentation that is important is that the whole point of this work is to step away from a global perfect map and really just emphasize only using local sensing. So the same kind of sensing that a human would have in these environments, where you can really just see what's around you as far as your eyesight will take you. We want to be able to use that to do our planning. So that's a really important part of our next steps. But we're gonna have to have like actual motion, at the very least, things in a somewhat realistic simulation to be able to do so.
Right. Now, in the interest of time, I'm gonna have to push on. Thank you, authors.
Hi, I'm Han Yu from Tufts University. I'm pretty happy that I got a chance to share my work, learning with dynamic feedback here. The first part, introduction. Reinforcement learning with human feedback has been widely applied in human-robot interaction field. We always try to get feedback that purely reflects the ground truth by using the simplest version of feedback, like binary feedback, or feedback that directly indicates what's correct or what's incorrect, to reduce the noise to improve learning. However, human feedback is dynamic. It varies from person to person because of emotions, personalities, and expectations about the future. Sometimes it is affected by contingency. The simplest version of feedback would not reflect these changes. Does these changes really slow the learning down, and can we use this redundant information to augment learning? In our work, we reintroduce the idea of scaled feedback to enable a robot to effectively detect when human feedback is changing. The methodology, we used Coulter's learning spiral model to describe the relationship between teaching behaviors and emotions. And we assume the variation reflects on three axes: consistency, bias, and focus. We also used policy shaping to augment Q-learning with human feedback. Then we run the experiments. Baseline methods are policy shaping with a naive classifier and policy shaping with a window classifier. The task is a building task in which the learning agent must build 4 distinct blocks in order. And the oracle we use to simulate human gives 1 feedback per 3 actions. The value of feedback is rescaled from the ground truth reward value of each action from the Markov decision process. And here are the results. We can see that PS window is better than PS naive in all cases. Conclusions and discussion. Based on experiments, we know that changes in feedback do decrease the learning speed. The degree of effects is different from method to method. For the naive method, a minor change on feedback brings a noticeable decrease. And since the binary feedback works, we also could classify scaled feedback into a positive distribution and a negative distribution. The learning agent might be able to be aware of noise in data or emotional variations in the feedback, based on established distributions. Scaled feedback is also able to show teachers' intention, which could be used to augment learning, especially in tasks with multiple solutions. Since in binary feedback, the action leads to a suboptimal result might also receive a positive feedback. But in scaled feedback, the best solution always gets the highest value. Thus, if we can get 2 well-established distributions, the scaled feedback might be better than binary feedback. Our future work would include studying the effects of bias, consistency, and focus separately, design a classification algorithm, and do a human-based study. That's all. Thanks for watching.
Okay, and do we have the authors here?
Yeah, I'm here.
Great.
I have a question, maybe I can directly ask. So can you explain about the building task that you mentioned in the video? So I understand that there are 4 distinct blocks that need to be constructed. How exactly did you conduct the task?
Yeah, it's the building. The 4 tasks must be stacked in order, which is like we have to stack the first box, then stack the second box. It's like a sort problem with some kind of restrictions. In the sort problem, you can put the number or the box, whatever you want. But in this task, you must put them in order. It's like you must put the block in the bottom, and then you can stack them up. Yeah. Does that answer your question?
Yes, okay, thank you.
Okay.
right. Again, in the interest of time, I'll push on, but I encourage people to discuss in the chat and after.
Hello everyone, my name is Kishan Chandan and I'm a PhD student at SUNY Binghamton. Today I will be presenting our work on guided 360-degree visual perception for mobile telepresence robots. So telepresence is an illusion of spatial presence at a place other than the true location. In particular, mobile telepresence robots help the human to perceive a remote environment along with the ability of moving and actuating in the remote environment. Telepresence robots are used in several application domains like offices, search and rescue, education, etc. Recently, researchers have equipped mobile telepresence robots with a 360-degree camera to perceive the entire sphere of the remote environment. To visualize the 360-degree videos, one can use a mobile device or a head-mounted display. The problem with using the mobile device is that it makes it difficult for the human operator to perceive the frame because of the size of device. Mobile devices are usually not designed to visualize such contents. On the other hand, one of the widely used methods of visualizing the 360-degree videos is using head-mounted displays. The head-mounted displays provide an immersive experience to the user, but the problem is that the human operator can visualize only a part of the remote environment. Typically, humans have a peripheral vision of about 120 degrees. Outside the peripheral vision, the human eye cannot visualize anything. HMDs are designed to mimic human vision system. HMDs also typically have a field of view of about 90 to 120 degrees. Hence, out of the 360 degrees, about 240 degrees is out of the field of view of the human. This results in the human missing the information available outside the field of view. The gap between the 360-degree video capturing and the difficulty of the human to process the all-degree view motivates our research. To address this, we propose a framework that for the first time equips mobile telepresence robots with the simultaneous capabilities of 360-degree scene analysis and guiding human attention to the areas of interest. The input to the framework includes live 360-degree video frames of the remote environment obtained from the robot. These frames are processed using an object detection system to output an analyzed frame. The detected objects are then filtered to highlight only the objects of interest. Depending on the robot's current task, the object of interest can be different. We can construct a sphere and use these equirectangular frames as a texture of that sphere. A user may only be viewing one part of the sphere at a time because of the limited field of view. The portion viewed by the user is called the viewport. At runtime, based on the head pose of the human operator, views in viewport are rendered accordingly. Finally, the framework overlays visual indicators in real time to guide the human attention towards the object of interest, while providing an immersive 360-degree view of the remote environment. This is our web-based interface that we designed using the guided telepresence robotic framework. I will now show the different features of the interface. The interface shows a 2D map with a live robot location. It also shows a window with a 360-degree video where the human can use an arrow to move around. To indicate the teleop input from the human, we highlight the arrow keys. A 2D icon shows the human head pose in the 360-degree view. The interface also allows the human to adjust the 360-degree view by adjusting the size of the window as well as the field of view using the slider. Finally, using the VR mode button, the 360-degree video can be viewed in a head-mounted display in VR mode. We have tested our framework in a target search scenario with television as a target object. We used a Segway-based robot platform mounted with a 360-degree camera. Now let's see the demonstration of our framework. The blue arrow shows the location of the target object. The robot is teleoperated by the human in the remote environment using a keyboard. The 360-degree scene analysis runs in background to find the target object in the remote environment. Once the object is found, visual indicators are overlaid on the frame to guide the human attention. The human turns the head based on the visual indicators until the object is found. Once the object is in the field of the view of the human operator, the trial is terminated. Thank you for listening.
Great. Do we have the authors here?
Yeah.
Okay, so I'll start off with a quick question. So how long does the processing of the image take before you can draw things?
So it takes about 300 ms to process each frame and find the objects in the frame, so it's less than half a second.
I have a question maybe related to that. Is it fast? Do you think it's fast enough that you can actually track some moving object, something that's moving behind you?
So when you are talking about tracking, you need a couple of frames and based on those couple of frames, you can track if the object is moving. Like you have to draw motion vectors on them, and then you can find the motion of that object. So given the current object detection framework, it takes about 300 ms, and if you want to track, it's too slow for the moving robot to track an object. But yeah, that can be an interesting way of looking at the problem, and maybe we have something that works for that as well.
Thank you.
Okay. We've got any other questions coming from the audience? All right. Then I'll move us to the last paper here.
My name is Avinash, and I'd like to present our work titled Distributed Reinforcement Learning of Targeted Grasping with Active Vision for Mobile Manipulators. We believe that the ability to grasp objects is essential for personal robots, especially grasping objects in clutter and the targeted grasping of unseen, possibly occluded objects. We aim to enable this using the reinforcement learning framework. Why RL for grasping? Reinforcement learning is data-driven and allows us to leverage deep learning. It's capable of learning complex pre- and post-grasp manipulation behaviors. For example, in order to grasp this green block, the agent has learned to push it and the other blocks away in order to grasp better. This was not encouraged in any way and learned simply through trial and error. Typical issues include the requirement of a large number of samples for RL to learn successfully. Traditional solutions include leveraging demonstrations, using multiple robots, or training in simulation, often with some sim-to-real transfer techniques. Our setup is applied to Toyota's Human Support Robot, HSR. The target is specified with a single RGB image to improve generalizability. Agent observation is an RGB image from a wrist-mounted camera. This is related to the active vision problem because the camera moves with the gripper. Note that no depth information has been used. The agent is also only rewarded on success, which makes this a sparse reward problem. Actions are either post changes or gripper open-close commands. We do large-scale training in simulation and then use a sim-to-real transfer technique to transfer the learned model to a real robot. This is a demonstration of our system. The top left shows the observation, and the bottom left shows the target to be grasped. We see that the agent is successfully able to grasp this soft black pouch, even though this wasn't a part of training. We believe this demonstrates the efficacy of our method. Contributions of our method include the building of a large-scale distributed system that does Impala-style actor-learner parallelism and scales successfully up to 128 GPUs. We built upon the QT-opt algorithm that did untargeted grasping with a KUKA arm. Our improvements include the use of frame stacking, which stacks 4 recent frames together, the use of hindsight experience replay, which allows the agent to learn from wrongly grasped objects, and mirroring, which lets it exploit symmetry and reuse past experience, and lower bound, which improves the speed at which Q values are learned. We also use an offline sim-to-real transfer learning method to robustify the extracted features. This is done by adding a feature matching loss between the original observation and one with randomized textures in order to make it insensitive to texture changes. The agents were trained to grasp between 4 and 10 objects sampled from the random and ShapeNet object datasets. They are evaluated on objects from held-out test sets of each. Which 15 objects, we were able to obtain a success rate of 44.6%. For context, this is an observation with 15 objects, and it was successfully able to grasp this purple chair. Our real-world experiments included a tray filled with 8 objects, 40 episodes, 5 per object, and achieved a success rate of 62.5%. We know that 11 out of the 15 failures were because it grasped the wrong object, and these mistakes seem to be between similar colors. Thank you very much for attending.
Great. Do we have the authors here?
Yes. Hello.
Great. So I'll give people a second to type in the Zoom. but maybe I'll start off with a simple thing, which is, in your view, so this is a pretty, thorough evaluation here. What are some of the one biggest remaining obstacle for putting something like this into someone else's home?
Maybe I can answer with two. Well, if you're putting this in someone's home, safety is the number one concern. And we have no checks in place so that it doesn't sort of spaz out and harm the person whose house it's in. And another thing is the lack of real world training data, which should be our next step.
Okay. And I see, Pitar, you have your hand
up? Yes, I have a quick question. So you mentioned that most of the cases when there was a failure, it was because the robot grasped the wrong object. Do you think it's possible to have a policy that actually detects the wrong grasp and then tries to re-grasp, basically, as part of the same policy rather than a separate one?
Right. This is actually something we've been looking towards, and there is work from Dieter Fox's group, I think, that does contrastive laws to sort of learn refine features over time. Things like this to help you re-grasp and identify them better is definitely something we're interested in.
Okay, thank you.
I would also have a question. In particular, are you using any imitation learning to bootstrap the policies that you have, or do you really learn from scratch?
Completely learning from scratch. And one of our aims was to make this as generalizable as possible. In the context of this workshop, this is the difference between academia and industry. So for us, human effort comes at a serious cost, and we do have access to resources. So we try to just throw compute at it and see what comes out of it without trying to tune it much.
And just to reiterate, how long did the training take in hours? Maybe just, you probably mentioned that, I just don't remember.
Using 128 GPUs, it took 4 to 6 hours, I think, 6 hours.
Okay, thank you.
I also have a question. So how does this compare to more classical approaches where, so I assume that you are just making the hypothesis that you only have the camera stream and you don't know in advance the objects or the objects model. Is that so? Okay. So, but how all this approach compares to more classical methods where, I don't know, you try to segment the object, identify, fit a sort of a known 3D model of the object, like even something simple like balls, spheres, parallelepipeds or whatever, and then you try just to grasp, fitting the model to the feature that you can retrieve from the images?
That's a great question. So that's what we were actually trying to explore with our work. How far can we push this by just giving it a simple image, which is why we tried to not model this. We even left out the depth information just to see if the system's capable just by trying again and again. And it seems to be doing a pretty good job. If we do include depth information, it gets quite a bit better. And I'm sure if we include more classical shape information and segmentation and things like this, it's going to get much, much faster and better in every way. But this was more testing the limits of the most generalizable approach.
Okay, I hate to cut off active discussion, but I'm going to cut it off so that we can move on to the panel. So thank you so much, authors, and I'm going to hand it back to Jeremy now.
Okay, so yeah, so we can start then this second session, which is the panel. Let me share quickly here. So this, oops, not sharing. Yes, yeah, now sharing. This second session will take 80 minutes from now. And again, just a bit of logistics here, how to interact. For the panelists, please keep your camera on and feel free to unmute and speak at any time you want. For the audience, I would say unless you're making a question, please keep your camera off and write your questions in the Zoom or the feedloop chat. And if you wanna raise your hand, if you wanna make the question yourself, please raise your hand and wait to be unmuted. And as I explained before, there's this option here, this icon in the Zoom app where you can press it and then you enable this panel at the right where you can raise your hand. And again, for people who came after, this session is being recorded. It's now being streamed in YouTube. So if you have some problem, maybe it's already too late, but still, you know, just let me know. Some of my questions may have a bit of a provocative tone because I think we have to, you know, try to keep this kind of interesting. And I think, you know, just don't take it personal. So for the panel, I'm really pleased to announce this panel because it's really like we could gather this number of people who have significant, I think, academic contributions in service robotics, but also the practical industrial experience in deploying service robots. And I think these are really will be great for us to discuss how to close this gap between academia and the real world. So let me just, instead of sharing this screen, let me just go through the speakers one by one. Also can confirm if they are here. So the first speaker, panelist is Leila Takayama from University of California, Santa Cruz. Are you here? Yes?
Yep, I'm here.
Okay, thank you for being here. Then we have Satoru Satake from ATR Japan. Satoru,
Yes, I'm here.
Are you? Yes, here. Nice, thank you. And then Peter Bill from UC Berkeley and Covariant.
Hello.
Oh, hi. Thank you. Carlos Selemin from TU Delft. Carlos.
Hello, everyone.
Can see you there. Surya Singh from Intuitive Surgical. Surya, yes, you're here. Professor Tetsuya Gato from Waseda University.
Hi, good evening,
Professor,
everyone.
Thank you for joining us.
Yeah.
Serena Ivaldi from INRIA, France.
Hi, hello, everyone.
Yes. Hello. And Henny Ben Amour from Arizona State University.
Hi there, everyone. Hi.
Ah, yes. Nice. Okay, so now that all the panel is here, let me just share the last time this screen because I want to start with some, just to get started, and hopefully we don't need this anymore after. But, you know, I started talking about that, yes, we want to, you know, decrease this gap. It seems this gap is a big problem and so on. But maybe the first question to ask, you know, is it really an important question to make? Should actually we try to, you know, try to decrease this gap between academia and industry? And I could say at least a few reasons why maybe we should actually keep this gap. So the first one would be, it's good to have a gap because it allows researchers to focus on the fundamental long-term investigations without worrying about the practicalities and you know, the ad hoc solutions and short-term industrial interests. It's also good that we have a gap because the metrics for scientific accomplishment and industrial accomplishment, they're different anyways. So maybe it's very hard to try to, you know, put these things closer. And also, you know, if I am a graduate student, I have to publish to graduate. And practical research that will involve a lot of system integration and trying to make systems robust and so on, they're just going to slow me down on my research and be of little academic value. So with that, I don't know if you guys have some comments on that. Like, is it really important to decrease this gap, or is it sometimes actually good to have this gap because it allows us to focus on the fundamental scientific problems? Anyone?
Maybe I'll jump in. So this is Peter Beal from Berkeley and Covariant.
Yes.
So maybe one way I like to think of it is that rather than asking whether there should be a gap or not, but a very related question is like, what should we try to achieve in industrial efforts versus academic efforts? And I think when we think about academic efforts, it's really about generating new insights. So, can you find something that you can then write about that will teach people something new and help them understand something that was not really understood before? And so, to me, often that doesn't necessarily mean building massive systems. It could, but it could. It could be that you need to build a large system just like somebody might have to do in industry, be able to get to that insight. But very often you can get to insights by looking at smaller data sets, smaller experiments, and still find something new. Whereas in industry, I would say insights are great and they might be necessary, but they're not really the end goal. The end goal is a working system. And so the way I see it is that even though what might be done can often have quite a lot of overlap, the end goals are just very different. Working systems versus new insights. And often that leads to a gap, but I wouldn't say the gap is always desirable. I think there are many problems people run into in industry that in academia people might not be aware of, not pay attention to, where there's a lot of academic research to be done. And so I think bridging that gap is actually pretty important. But yeah, at the same time, building a self-driving car in academia, I don't think in academia you would pursue the route of, can I get 1 billion miles of data collected? That seems more of an industrial effort. In academia, you'd probably look at what are the missing pieces of the puzzle that might be necessary in that context, but I wouldn't necessarily expect an academic lab to go collect 1 billion miles of, driving.
Mm-hmm. Yes, that's very.
So maybe to chime in here after Peter. So I absolutely agree with Peter. And at the same time, I also think there are different types of gaps. I think when it comes to human-robot collaboration, we have the wrong kind of gap, and that we have fairly little at the moment connection to industry. I think this connection could be strengthened by having also better benchmarks out there, by releasing our code, by having platforms that we collaborate among each other with, because then from time to time industry could latch onto these benchmarks and these simulators and so on, and try to figure out what the current state of the field is, and maybe already use some components. Because the field needs to mature in some parts for that mature component to then basically be integrated into industry where the TRL levels are much higher. And so I think that's one of the things that we're missing, is that even for us to kind of collaborate with each other, we need a better way of expressing this collaboration and enabling such a collaboration through benchmarks, through simulators, through releasing our code. And I think other fields, kind of the deep learning field, for example, has been doing a much better job at kind of releasing stuff into the ether so that other people can from time to time kind of latch onto that and figure out whether they can use that for industry or not.
So maybe I'll take on to that. I think you're correct. When you pick a simulation or a benchmark, it helps people collaborate, which is a good thing. Perhaps I'll tease that the division between industry and academia is a bit of a false dichotomy. Everyone wants to do novel things. I mean, industry advances on the back of novel methods that solve problems for clients, and hopefully, in the case of industry, have a product to sell at the end or service. I agree with Peter Abil's comment here that the goals are slightly different. I think that's a nice way to think about it, actually, is what is, if you want to say, is the reward function that we're trying to optimize. And there's certain tasks which are clearly industrial, and those data sets can be made useful, but then to some extent the general person or community or company generating the data set has an objective. So if I'm generating 1 billion miles of self-driving vehicle data, then that might not help me make a robot that solves, say, self-driving trucking, for example. It might or may not, I'm just making it up, or it may not help me solve some other more general case. So I think we need to pick those things carefully. What's really cool to observe from the open source community is that making open source tools helps everybody. not just close the gap. It just helps everybody. So I agree with that.
Mm-hmm.
And actually, there's one thing I was going to say. Industry sometimes gives people freedom in a way academia does not. Sometimes there's this kind of myth that industry locks you down, and it does sometimes. So, for example, in our last paper, the gentleman said, "Oh, I didn't want to use some pre-trained data set, or I didn't want to pre-classify things." M-Turking is totally allowed in industry. It might not be the cool thing to do in academia per se, because again, it comes down to the goal. If your goal is to come up with novel methods, as Peter pointed out, then yeah, that's not the same. But if I can buy or do something in industry, why not? It's totally allowed.
Yeah, I'd just like to build on that idea. I agree with what everyone said so far. And this idea of M-Turking your way to a solution or a product or a service is a place where I think service robotics in particular sees a gap between industry and academia, right? So if we look at most service robots that are actually deployed in the real world at any kind of larger scale, there's usually humans in the loop. We usually hide that in the marketing materials and VC pitches. And actually, if you look at the human-robot interaction research and service robotics, we're working towards full autonomy, whatever that means. But actually, there's a lot of Wizard of Oz used, and we just call it something different. And we have big debates about whether or not that's cheating. But I think it is a practice that's worth acknowledging, right? Because if there are humans in the loop, how are we going to do that better, right? We have service robots that have been running on shopping malls for years, and usually there's about one operator per 6 or so robots, because natural language processing is hard, right? And understanding what a child is saying is hard when they're far away from the microphones. And I think those real problems are things that are not going to just be easy to erase. And so I think one challenge in service robotics in particular, because they require social skills, is integrating those humans in the loop on both sides of the gap.
So probably I will also add something that has been already said also by Peter. Maybe having gaps are important in some of the domains, but maybe in some others it is good to close them. For instance, all of us, we would like to have soon service robots already deployed in our society, helping, for instance, the elderly, or in the hospitals, or in situations like now the COVID applications, for instance. But so if the academia were closer to the industry, so all the developments of all these smart people will be like adding something to what they have, right? But it is also true that if we close all the gaps, it will mean that in academia we'll have to be doing some work that doesn't add much value in academia. Like, for instance, as Peter said, like if we have to do effort for, I don't know, collecting a lot of data for the autonomous car in academia to be just completely close to all the experience that industry has. So we will have to do a lot of effort with our PhDs, master students, postdocs, etc., doing something that maybe we don't give much value in academia because it is just engineering from our perspective. So maybe having gaps in certain domains is important, but closing them in others it is also good.
Okay, nice. I think, yeah, that's, I think I actually have something that's maybe related to that. Yeah, let me just go with this next question then, because this came from Jethro. I'll read his question, and he's more like closer to the industry, to the productization of the research outcomes. And he pointed here, he said, how can we bridge the benchmarking gap between academia and industry? Maybe 99% of what academia thinks is good enough or robust enough is nowhere near usable for industry. Lots of domain knowledge seems to be missing, but also not really fed back into academia. I mean, the research that we do in industry don't go back to academia, if understood correctly. And if academia does not know what industry expects, then academia will forever think they're doing okay. So it's hard to solve a problem until you notice there is a problem. So I think this is also a big part of this gap, right? There's no, yeah, maybe academia is a bit kind of, and Jethro, feel free to, if you wanna also expand on this question, since that's your observation. Yeah, it's kind of, are we doing research in academia that's maybe a bit blind to what's happening in the industry? And at the same time, maybe is the industry, you know, have some responsibility on that because we don't interact with academia and don't feed back this information of what we are doing back to academia?
Maybe to chime in here, so obviously kind of there is a gap, and that's what we're discussing, but I also want to say there's been a ton of interaction between academia and industry, and just kind of speaking for myself in my own lab here, I have connections with a number of companies, Intel, Honda, kind of you name it, and we are closely working together in a number of fields. I think there's substantial information flowing in both directions. At the same time, kind of the challenge is really tricky in that kind of companies, there is a limit. So even if they want to kind of talk about what they're currently doing, there's a limit to that. And that's often coming from kind of a higher administration. That's not the scientist or the researcher, that's kind of the boss at kind of 2 or 3 levels above that. And so we have seen this challenge in that we want to collaborate with each other, but of course there's a limit on what they can share about future developments, IP, and so on. So that's certainly an issue, but it's not because people are not talking to each other, but because of legal issues. So I certainly want to say that there is substantial interaction, especially now with more and more startups coming up. I can see that they're, for example, kind of in our case, they're reaching out to the lab. I've been collaborating. I remember in one case, a company in Los Angeles, a startup, they asked, hey, do you want to come over for a summer and just hack something together? And we did exactly that. I kind of just drove down to Los Angeles and hacked something together. It was actually really nice so that they could see the current state of the art. So again, there's certainly been quite a lot going on, but the challenge is also really large and kind of difficult, and there are legal kind of impedances with regards to IP here.
So I'm some kind of the agree. So it's a connection between academia and industry. One important thing is some having a good application here for the company, for having some good application. Sometimes it can get the monies, and especially the company want to the new field of the application. I think the academia something helpful to the finding out to the new field. But so sometimes it's a champion data. It's a data is huge. It's in some kind of the site to finding the new things. But the next step is necessary to the more stable big data to between the gap. So to do that, it's necessary to share some kind of the good application, good service robot system, and keep these connection is very important, is my impression.
I think one of the challenges, right, is that when you work in industry, your company wants or may need to have a competitive advantage, and so the IP lawyers don't really want you to share everything you're doing for good reason. And so one challenge is, if companies are putting out products, services, and patents, let's say, and in academia we put out papers and demos, right, and talks. Somehow we're just not talking to each other quite right.
Yeah.
And so I think one challenge that's out there is how do we share, right? And if you look at business schools, they put out case studies sometimes. You embargo the study that you ran in industry for a few years and then you publish it later, right? Once you've taken advantage of that competitive advantage. I think that's one way. Open sourcing code, of course, I strongly believe that's a great way to share and to put your stuff out there so others can build upon it. right? And you don't have to share your proprietary data set, right? But you could share the tools that you use to get there. I think coming up with other ways to share across the gap is going to be important for us to make progress, right? It's really sad when we're all working on the same problems and not able to talk to each other. So openness and figuring out how to do that is key, right? We don't want to just write papers that go to all of like our friends. You want to write papers that get somewhere, and ideally solve a real problem.
Yeah, I think it should. Yeah. No, sorry. Yeah, please.
Please. Well, I'd add to that, right? I think it's about, if you share things together, you get insights. Actually, the comment I'll note on open sourcing is it actually makes you a better developer, because somehow in the back of your mind, you can't hack as much because someone else will see it, if I may. Perhaps I'm speaking about myself. So I think there's another thing I like to think about it as a kind of lens, which is basically what you want is intellectual freedom, right? Companies have to have some intellectual freedom to make the novelty, to have a competitive advantage to begin with, right? And I think maybe it's also just understanding what each company sees as special and not, or industry and so forth. So in a company, certain things are trade secret, or for example, who their suppliers are, which probably doesn't mean much to by an academia. But some things are quite are trade secret, which means something to someone in academia, are the data set. So being able to somehow separate it or come up with ways to, as Leila said, kind of work on parallel problems so that people can actually gain the skills. So in a way, to borrow the terminology of RL, you can kind of shape the policy even if the data isn't there, is an option I think it's worth thinking about. I'd also add that sometimes it just is useful just to get people to mingle, because sometimes each of us takes things as assumptions, even if they're not. So as I'll speak from sort of the intuitive lens, a common myth, for example, for a surgical robot is it's just the robot and a surgeon. But it's actually a collaborative problem, because around the surgeon are anesthesiologists, there's a nursing team, there's a prep team. The room is got full of people. It's not just one-on-one, but the typical myth is this thing. So I think somehow we need to actually just talk more, which I guess is what we're trying to do now, just to have people put their assumptions in check, right? I think that also helps you understand things, because understanding the requirements of industry helps shape the assumptions you take, which might actually be a novel contribution as a research path. Sometimes you just can't assume the world is square, even if you'd like to, for a particular piece of theory.
Okay, so I think, yeah, let me, we have a question actually from the audience. So let me just read the question. And I assume if people didn't raise their hand, it's because they want the question to be read. Okay, so just read it. So how can the academic robotics community do better to reward research that addresses relevant problems and avoid seeking novelty for novelty's sake?
I think some of the challenges that corporate teams have been putting out are actually really interesting, or the NIST challenges, right? That try to provide real problems to chew on in the robotics community. Those are one step in that direction. RoboCup at home. Yeah.
Yeah.
So jumping in here for a moment, I think the challenges are great. I think they've inspired a lot of things. So for example, if you look at Amazon Picking Challenge from several years ago, it was clear that was an important problem to Amazon. Right now, it's an important problem to pretty much any logistics company in the world, but it was at least publicly presented as important first by Amazon, and then it grew from there. They're not running the challenge anymore, but the problem was put out there as a clearly important problem. And I think that really helps when there are these challenges, whether they are explicitly run or just put out there maybe in a description of these are the key challenges we face as an industry. I think when you look at maybe the subtle differences, going to Chris's question a little bit, the subtle differences that at least I find, while seemingly subtle but very important in practice, is in industry, it seems to deliver a working system, there is two things that are fundamentally different from how typical academic research is done. And maybe that doesn't have to be the case. And maybe we can find ways to bridge that gap. But I would say the two distinguishing factors are, one, that when there is a benchmark or anything like that, usually in academia, people let go of the benchmark once you have, let's say, 80%, 90% performance. Because the thinking is, there is a thinking behind is that once you're 80, 90%, the innovation that's remaining is not that much anymore. We're pretty much there. But when you work in industry, you realize you need to deliver 99.99% type systems. A lot of the challenges come in those extra nines that academia doesn't pay much attention to today. And I think that'd be an interesting thing to possibly change, think through, what are the right challenges academia could also look at, where you really keep pushing till many nines of reliability. And sure, if all it is data collection, then maybe that's not the right thing to do in academia, but often there are other challenges that come up to ensure that you, let's say, collect your data efficiently. Don't waste time collecting uninteresting data. How's your system smart enough to explore it the right way to get those extra nines and so forth. So that's one thing, like keep going well beyond 80 or 90%. I think there's a lot of insight that should begin there, but it's not a cultural thing right now. Another one is that to write papers, often it's the expectation you isolate a problem and make progress on an isolated problem. And it kind of pigeonholes you a little bit. In contrast, to solve a problem in industry, you are willing to do anything pretty much. Like Syria was alluding to, Mechanical Turk, getting more data annotated, right? Or is it human in the loop that helps solve a problem that in academia you might want to do fully autonomous, but now human in the loop is good enough. And so this notion that there's a whole system you're trying to get to work and that there might be many, many components to it, and that it's in industry you push on the component that is the biggest gap right now, whereas in academia you might have a fixed component that you're excited about, let's say full autonomy, make that as good as possible, and in the process ignore the other components. And so I see a gap there that I think could academically be addressed in many ways, to have intelligent systems that actually self-identify where the biggest gap is, that autonomously decide that more human input is required, or more data collection is required, or more annotation of a certain type is required, and so forth, rather than keeping that onto the human designer. And so I think there are things we can work on in academia. Even if we will not get to the ridiculous amount of data collected, we can study the processes that underlie doing that much more efficiently.
Just building on those ideas, workshops like these provide a venue, I think, to have these kinds of conversations, which is nice, right? A lot of times the peer-reviewed papers that are presented in a conference are academic papers. Sometimes they're industry, but mostly academic. And I think maybe even thinking about new categories of contributions that can be made in venues like this, right, would be good, right? Usually we put them in panels or workshops, but how do we enable industry and industrial research to get shared, right, in a way that counts for them, that they get brownie points for, and performance review brownie points for.
Yeah, I think actually I had some question that goes into this direction. And this also, it's based on a comment that one of the members in the audience made. Like Gonzalo says that academia should rethink its role in robotics and shift its focus towards system robustness rather than novelty. Change conferences, journals, and grant evaluation systems. So I think this is a bit maybe too radical, but I have something maybe a bit more like narrow related to that, which is honesty in papers. Like should we talk more about explicitly mentioning what are these limitations of the methods, and discuss the assumptions, and discuss when it fails. And I feel like it's always a tricky thing to do because it's a way to get rejected. I think you get the lazy reviewer. He will use all these flaws that you explicitly mentioned to reject your paper, and then what can you say? And in general, I think it makes the paper looks weaker, let's say. But I think from the industry perspective, I think it's very good because it gives the practitioner like realistic expectations. When you see a paper that talks a lot about what are these limits of the method, then yeah, maybe you as a person in the industry, you have much more information. And I think, yeah, maybe this is one, yeah, I think it's related to what we're discussing before, like, is there a way, can we reward, papers that are a bit more honest? And
but this is interesting not only for industry but also for academic researchers. How many times have you taken a method published by a colleague, and on the paper it seems to be very easy to implement and that it works, and then you discover that it requires hours of specific robot tuning with very specific knowledge that you don't have, and so you cannot even make a fair comparison. And if you try to do a fair comparison, at some point you have to stop and compare with what you were able to achieve, because from the paper you don't have all these little details that are what makes the difference with the robot. And I mean, in my experience, this worked also when replicating works that were done with the same robot that I was using. Even, I mean, same robot, of course, each robot it's the same, but I mean, each platform has the little settings that make it unique. But this is the kind of information that is actually very difficult, and it's put like somewhere in the discussion often. And it would be really like useful to have it. That's why I always try to push for having, like, to publish the code that they use to do the experiment, because usually there is a file where you have all the parameters, and so at least you get the same parameters that they used.
Yeah.
And that allows you to do some comparison. But most of the time, I mean, as a reviewer, when I ask, they say, oh yeah, after the paper is accepted, I will publish the code. And then if you contact these people after some months, they say, I didn't have time, the code is not polished, and so on. It's a shame.
I totally agree. And I would say it's not science if it's not replicable, right?
Exactly.
Like, we should be holding ourselves to that standard. It needs to be replicable. Otherwise, what's the point? And same with our demos, right? We should probably say in our demos, like, these days we've gotten better with saying this is sped up by 4 times. But maybe we should also say, oh, and the lighting needs to be this way, and you can't use any glass, right? Yeah. Being more specific about where these things work.
That's true. Even I'll add, if it's not replicable, you can't sell it by definition.
Yeah.
It's not a product, right? So I completely agree with that comment. And I think it's a cultural thing, right? You just have to be transparent and say science is about being replicable.
So going to the point of the question, I think that it would be interesting and more efficient, not only for industry, but also for academia, to talk about failures. So we normally have ideas that we come up with these ideas, and then we go to the literature, and probably someone already had this idea and implemented it, was successful. But sometimes when we have this idea that hasn't been implemented, we go to implement it, and then we fail, and then we have to start thinking how to improve it. But then when we have the paper, we just talk about the things that work, right? We don't show all the other models or methods or whatever that failed in our process of research. But what it means that what will happen is that in the future, other people that will think in this, they will again go to implement this because no one has tested that, at least no one has published or shared these results. And then there is a lot of people repeating the same effort. So because we are not sharing this experience. So if we did this, then we will save time for the younger researchers or other researchers in other labs that will not repeat this. But I know how to do this. So one thing that I could think that we could do, I mean, there are a lot of people that are posting blogs or websites in which they somehow explain their papers in a faster way, like going to the point with videos and plots and or slides. Also for advertising more these papers. There we could talk about the failures, because someone that is really interested on this could go and see like more details. And for failures, we don't need the peer review part, right? Like we need the peer review process for testing or trying to convince someone that is expert that our method is successful as what we are trying to show with our results. But for the failures, I think it is easier that people will rely on something that is not peer reviewed. So I think that could be an option for trying to share this information that will make it more efficient, but in both industry and academia, I think.
I like this idea. I'd like to add one thing that there's a positive precedent for this actually, even though it doesn't happen too often. There's a robotics conference called WAFER, Workshop on Algorithmic Foundations of Robotics. And I think since the 2010 or so edition in Singapore, it's become a tradition. Well, one presenter there had a dirty laundry slide at the end of their presentation. And since then, it seems like it's become a tradition for more and more people, and even requested in the later editions for every presenter to have a slide at the end to expose their dirty laundry behind the project they just presented. And I think it's something people in the audience very much appreciate and gives a lot of additional insight, and not necessarily in a way that takes away from the contribution of the paper. In fact, it makes it even more clear what the contribution was. And to earlier point, I think it was Carlos, maybe people are worried about, is their paper accepted or not? I think even in a paper that you submit, you could highlight limitations that make it stronger, but definitely once it's accepted, it's too late, right? So it's already in. And so it seems like there's really no fundamental limitation there to share a bit more detail on, oh, maybe it's the lighting condition had still to be such and such. Maybe it still needed a green screen. Maybe it's still sped up now, or things like that. I think those help a lot, and better appreciating the work.
Yeah, I think showing how hard it is to make this stuff work is a good thing. For customers too, right? They expect, bipedal robots to run up and down stairs because they've seen videos of that, but we don't show them the hundreds of videos that came before when we failed. And maybe we should have a bloopers video session, right, in the conferences, this is hard. And it's being honest about it, but it's also, setting expectations.
This is, if I can say, in humanoid robotics, we always get these comments like, oh, I've seen Boston Dynamics jumping and doing somersault. Why is not your robot doing that? Like, it's feasible. It's solved. The problem is solved. So why is your robot so disappointing?
Yes, service robots get that all the time. Yeah.
I think the bloopers video is actually a cool idea, and a colleague of mine actually did something like that for his PhD thesis, and it was amazing. You could see like hours and hours of the robot failing and kind of doing the wrong thing, and that gives you also a better idea of which components made it fail. Sometimes it's like a collision detection error or something, or like the light was switched off. And so I think that's actually a good idea that, again, like similar to also what Peter said, doesn't take anything away from your achievement.
Right. If anything, it makes it more special, right? They understand why we're cheering so much when it finally works.
Yeah.
I think
it also gives, go on, please.
Just to echo Carlos's point, right? Like identifying those dead ends is valuable.
Yes, exactly. I think it also helps give you insight on what assumptions you might need to research next. So to pick on the glass, right? Why is the glass a problem? Is it the specularity? Is it the fact it's transparent? Whatever it is, those are interesting generalized questions.
May I have one comment?
Oh, yes, of course.
Yeah, so it's about some previous talk and discussions. So now I'm collaborating with some companies like this. You can see in the background, and I'm currently thinking so academic study and for this kind of application, industrial robot is different for me. So working in parallel. So actually, these robots using deep learning. But this original idea comes from the very old study of the neural networks in the developmental robotics, cognitive developmental robotics, my old studies. So I know that it works. So a company now replicate it and try to make some product. So academic study too actually, as you mentioned, always aims to find the new findings, new goals. And this is one of the applications. So I think there are big gaps. But at the same time, based on the experience of the collaboration, I found that there's something interesting. So industry researchers find new application, new problems through the just replicated our studies. So in that sense, I think one of the just challenging the difficult task. So without many new methods or new application, new neural networks model or something, but just try to new difficult task over try to tackling, then we could find a new research theme. So in that sense, I think the collaboration with an industrial company is very interesting and very impressive for my research.
Yes, thank you. Thank you for your input. Yes, I think, I definitely agree. I think it's usually a lot of people, I think, worry a lot about how to, show that their method work, but a lot of also people, I think, instead of looking from the method and then try to show how it works, is what is the problem that actually it's a very hard problem to tackle, and that would definitely lead to the development of new methods, right? Yeah, so let me just, let me see, I think we have, okay, I think, yeah, sorry, I will skip one of the questions here in the chat because I think just to keep more continuity on this conversation, like, yeah, still related to this this idea of having papers, which we don't show everything, and I think Peter in his talk in this supporting material, he talked about this thing that in academia we tend to consider 70% as the good outcome of success, and then we move on to the next big problem. And then, of course, in the industry, we try to push this. We have to push this to the 99% of success. Otherwise, it's not useful. But as for, I think most of us here are like advising students and have these companies also. So for Peter, for example, you have Covariant. How do you pick? How do you know which paper? How do you advise the people working for you? For example, if you see all these bunch of papers in archive, maybe they're all of this kind of 70%. How can we identify the ones that would have the hope that if we work on the top of it, we can bring it to the 99?
Yeah, it's a good question. I mean, there's a lot coming out for sure. It's hard to keep up with everything, though. If you have a larger team, you can distribute the work a little bit, or you can hope that, automatically in a distributed way, the more interesting things bubble to the top. I think there's a couple of things that at least I tend to check for is, so first thing is, there's a new idea, but then how is it validated? So, I mean, if it's a new idea, and then if it's, let's say, a computer vision idea, and the evaluation is only on MNIST, then you're kind of like, okay, that's not really up to today's standards, and that probably means they tried it on CFAR and ImageNet, but it didn't work, or maybe it doesn't scale to those kind of settings. The idea might still be, the start of something, but it doesn't look, I would say, like very, very proven if it's not evaluated on the standard settings. Similarly for a reinforcement learning idea, if somebody evaluates on 2 out of the many environments in OpenAI GM or DeepMind control suite, it immediately makes you suspicious. Only 2 out of many. What's going on there? Once you run on one, it's the same interface to run on all of them. Why isn't there a more complete evaluation here? So there's definitely the kind of quick flipping right away to the experiment section to see what was it actually evaluated on. Now, that is a way to identify the things that are already proven by somebody else to work. It is always possible that the idea is good, but people didn't get around fully evaluating it, and then you kind of have to independently just think through the idea and see, okay, what is it about this idea that maybe we still want to try and evaluate it ourselves? But it's a little less likely to immediately be picked up on if the authors of the paper didn't do the more complete evaluation themselves. Now, even those evaluations, you could say it might be overfit. I mean, if you, let's say, look at industrial bin picking or order picking, the kind of imagery your robot encounters is very different from ImageNet. But at the same time, I would say a lot of it in maybe machine learning type settings is alleviated by the notion of train and test sets. There was a question about how do we build more robust systems and evaluate them. And I think the beauty of at least supervised learning applications is that there is a very explicit notion of train and test. And so the fact that something works well on a test set is some measure of robustness of the method. And so that helps a lot. Unfortunately, it's harder with physical experiments to have as explicit train and test environments, but maybe that would be one of the things that would, if you think about what could help a lot in terms of immediate credibility of a paper and seeing it, quickly picked up on an industry as something that's promising, if there's really that notion of generalization. Because almost never will the academic environment be the industrial environment, but if it already has a train and test notion, then it might carry over relatively well.
Does anyone want to add on?
But if I can just reply, I mean, I agree with what Peter said. Just that I'm not very comfortable with the idea. Actually, I disagree with the idea that in academics we stop at 70 or 80%. I mean, maybe it depends on applications. Maybe for computer vision, if you have to identify an apple on the table, it's not that critical if you miss it once. But if you do control, you cannot stop at 70%. 70% for a human, it means the human, it falls. It's hundreds of euros of dollars of money that are crashing on the floor, and you have to spend in reparation, and this is not acceptable for us. So if you're flying, you cannot let the robot, crash. If the robot is walking, it cannot stop and crash, and then it's a catastrophe. So I disagree on 70%. I think what we aim, at least in humanoids, even if there is a lot of dirty laundry, as we said, and also tuning, but what we aim is to have something that works all the time, and this is difficult. That is why we need to expose the dirty laundry. But it's I think it's at least in robot control. I see people that are putting really a lot of effort in trying to make things really work on very complicated, complex platform. And I mean, I don't know if it's the same in machine learning or computer vision or other communities. For sure, considering what I do, if I see a paper with a new method only in simulation with an inverted pendulum, I don't know, it's like it maybe, I don't know, it's not the same as seeing, okay, my method works on making Walkman walk and jump, or seeing Boston Dynamics robots doing a backflip. It's not the same, but I think it's especially in robot control, we're trying to really do having something super reliable.
Yeah, I think maybe that's related that, in real robot control, you don't have this scene to real gap, right? You just have real, and you have to make it sure that it works.
But there are some things that you can develop in simulation. There are also like a combination of control with machine learning that you can prototype, and you can exploit simulation with domain randomization, with other techniques to explore how you can cope with uncertainties and difference in the models and so on. And for this, simulation is a good tool. I'm not saying simulation is bad, but at some point it has to work on the robot. Otherwise, we do computer graphics. It's not robotics.
Yeah, sometimes I see this comment like robotics papers, they look like SIGGRAPH papers or something.
Well, okay. So 2 comments on that. One is I agree that clearly things have to work. Otherwise, it gets out of control by definition. I think when we say things are robust, has to be in context, because the other way you get the robustness up is that you make the context smaller. We do this, and then I see industry does this all the time, right? We tell the customer it'll only work, under this and this conditions. And then it's and sometimes, of course, the extreme is obvious, right? Your car will only start on, February 29th on a sunny day, then you're never going to buy the object. But to be clear, there's a trade-off here, right? I think what you want is for it to work under those conditions, and for that set of conditions to be expanded to what solves the problem. In the industry, it's probably what solves the need, right? So to pick on a Da Vinci, as long as it does a surgery, whether or not it helps you fold up laundry, it's still a product, I hope. But I think I'll point out something else, right? The sim to real gap can help a lot of ways because the simulation, not the sim to real gap, but the simulation helps a lot of ways because it helps the engineers and the academics make progress, right? Just for example, to pick on the car industry, they simulate car crash all the time. And luckily that means we get better cars because they don't have to actually do it by experiments. So simulation is really useful. And I think that's also something we should try to help provide tools. That's a way of doing the collaboration. So I completely agree. And one other comment I'd make, actually, sometimes in industry, back to this notion that I pointed out, you can do things until it works. The same thing is true for controllers. You can get an army of engineers to tune a family of PID controllers until it works. So it needs to be stated what's going on. And that's also why I think it's important for everyone in an industry even to be a little more open and say, this is kind of what's inside the box. I can't tell you what, for example, all the parameters are, but I can tell you this is the nature. And to some extent, back to the comment Peter was making, yes, when you have experimental evidence, it's clear to understand. But sometimes if you don't, that means now you as in the sort of independent party have to decide based on the idea, I have to extrapolate, right? Where in the previous one, I could interpolate. Now I have to extrapolate, where is this idea going to go? But yeah, I think these are very valid points. Clearly, if it falls 3 out of 10 times, it's not helping anyone. But it could be insightful. So maybe it's still helping someone.
Yes, from my experiences, it's true. Yeah, actually, the company helped us to improve the performance from the 70-80% to the 90%, which can be shown the demonstration in the multiple exhibition. Actually. So yes, especially in my case, I use only the real robots for collecting the data. So in that cases, and so companies have strong power to collecting data using real robots. So yeah, actually, so such kind of the collaboration is very helpful to improve the matter study.
I mean, I think back to the 70 to 90% gap, and it comes down to what was done to get from one to the other, right? And I think the key is novelty and understanding of method, which is what advances the community, regardless of which side of the camp, quote unquote, camp you sit on. And because sometimes even if you can, quote unquote, beat it with a hammer and get it to work, normally there's not novelty there. I mean, we kind of know that is an approach. What's a question to ask is, did going from 70 to 90% involve doing something else completely? And that could be an interesting contribution, whether it's a new algorithm, new method, and so forth. in addition to, or just for example, how do I make a controller robust? So Peter mentioned this great idea, which was as I'm collecting data, I now have some logic or method which says, should I go ask for more information? And I, as a person, do this all the time. Imagine I'm interacting with you and you tell me something and I don't know. I'd say, can you please clarify? This makes a lot of intuitive sense. That kind of insight is critical to know how you got from 70 to 90%, for example, or 100%, whatever, as close to it as possible.
So I think it's a simulation is very good for the connection between the academia and to the industry. The one thing, I'm basically working about the human-robot interaction, basically in the working about in the real field. In this case, we meet new situations, like we put the robots, the children abuse the robots when it's happening. So we collect the data for the academic field. Then we can create some kind of equation, something. These kind of the equation, the finding is possible to the feedback to the industry, to the using the simulation. So this is very good. And also the research in such a kind of field, exactly the robustness is low. We try to find new things. We find to some good models. In this case, we develop this module, the try and error, and it's sometimes an unreliable thing that something that happen. But we only describe in the paper something, we only focus on some specific things. This is only important for the proof, the idea of the models, but it's lack of the robustness. But the background finding situation to the feedback, the industry, to the helping and developing, this is very important. So one thing is so feedback such a kind of situation from the academia to the industry by simulation is a very good idea. I completely agree with that.
Right. So let me just address one of the questions that we got here from the audience. So Mike Chung, he says here, as this venue is a unique place where we can meet the academics who also have rich experiences with industry, I'm curious, what are the ways to make more companies interested in showing up, presenting and talking in venues like this?
I just want to add one thing that I don't see too many faces from industry in this workshop. And I was sort of, well, I could be wrong. I don't know everyone. So that was where my question was coming from.
Yeah, that's a good point, actually, because when we started the concept of this workshop, I wanted to have like a half-half academia and industry, and yeah, it's very hard actually to bring the industry.
One tactic is to tell them they're going to get to recruit great interns. And then they can justify it as an expense against recruiting.
Nice, yes.
But yeah, it's hard to incentivize making time, right, for this.
Oh, I think we have someone. Yeah, Dan.
Dan, go for it.
Go for it, yeah. Can I answer as an industry person? Yes,
yeah.
Please.
So as an industry person here at this workshop, the way I had to pitch it was, as Leila said, you get access to good talent. Also the fact that this is virtual and relatively cheap made it really easy to convince people to open their wallet. And the third one is, how can I take the ideas that I'm going to learn at this workshop and apply them to our current products immediately? And so the key is being immediate. I come back and say, hey, I got this really cool idea. It'll take 2 years of research to turn into a product. That doesn't fly. If I say, I heard this paper, I heard this great talk, I think we can whip something together in a month and see if it can be useful to us. That's key. So lots of the idea of success here, how easily can I replicate the work? What are all those secret twists and tweaks that I have to make to my robot to make this system actually function in the real world? Those are the things that as industry I I need to hear about.
So I was reading that question almost the other way around initially. I was reading it as, how can we get people from industry to come and present more of their problems? So the other direction of communication. And my sense is that there's a big barrier presenting the exact problems you're working on in industry, because often the problems you decide to work on are driven by a lot of interaction with potential customers. And so you spend a lot of time with potential customers, understanding what exactly they care about. This kind of goes back a little bit to what we discussed about, do things work 100%, not 100%? You try to identify a regime in which things can work close to 100%. And at the same time, even though the regime is more narrow, it's still very relevant to potential customers. And so a lot of the effort goes into that. A lot of effort that might go into, might it be designing an end effector or a camera system or a software system that is really related to all that market research you did. And it feels like losing a competitive advantage coming out and saying, hey, this is the exact problem we need solved, unless you're already far ahead. And so I think the places from where it's easier to get the industry speakers and share the problems they're working on is companies that are so far ahead that there's an entrenched advantage they already have. Like, for example, when Amazon came out with Picking Challenge, they already control that entire logistics chain. So at that point, it's more comfortable to come out and say, hey, here's an important missing piece, because it's not like somebody by just solving picking can directly compete with Amazon. No, you have to do a gazillion other things to actually be a competitor with Amazon, right? You're just doing this one component. And so I think at the bigger companies, it might be at times easier to get people who want to expose problems that are important to those companies, maybe even from discussion generate benchmarks around them. So I think that's one angle. Another one is that if companies feel that the real advantage is in the data that they're able to collect, and that saying what they're working on is not so important because they have a unique data advantage anyway. And so I think that's another place where if you see companies that might have clear data advantages, it might be easier to convince them to come and talk about the problems they're facing, processing all that data, doing interesting things with all that data, because other people can't compete anyway, yet at the same time, there's very interesting intellectual challenges that can be exposed to a much wider audience.
I'll briefly add to that I completely agree. And to some extent, the potential market that you're going for is as much a trade secret as who your vendors are currently. And also, in a way, people don't live in a vacuum, right? So if a company says we're going in this direction, or this is my problem, in a way, they've kind of hinted what they're going to do next. As a matter of fact, even technically speaking, when you put out a job advert, you try to write it carefully so you don't give away the market that you're going for, right? Because your competitors are actually looking there also.
Just one thing I actually wanted to highlight that we haven't really touched upon, and that is in one of the questions, which is I would say there's maybe two types of industry, or industrial positions, which is quite different. I think some industrial positions are almost indistinguishable from academic research labs. And the reason I'm bringing this up is because one of the questions is about internships and so forth. And I think thinking about internships and really being exposed to problems that are different in industry than academia, I think some internships you go and let's say you go to maybe Google Brain or Facebook AI Research or DeepMind. Those are maybe the best way to think of it is extremely well-resourced research labs with a very similar agenda to academic labs, meaning trying to really focus on novel insights and not necessarily needing to solve problems that directly tie to the company's bottom line in the next half year, or even couple of years, right? And so if you're looking to get exposed to what it means to do research with way more resources, then that's a great, different experience. You can learn from different people also. But if you're looking for, what are some of the struggles of putting robotics in action in the real world, then those are not necessarily the internships that are going to teach you that. You're going to want to work in more of a product-oriented group and see what the struggles are there.
Okay, so yeah, so I think we still have a lot of questions, but time is running short. So let me change a bit on the direction here. So I would like to direct this question first towards like Serena and Leila and Satoru primarily, and of course all the panelists. Please, you can give your input also. But Leila, she worked with psychology and the empathy. She talks in her work about the empathy between humans and robots. And Serena talks about usability, trust, acceptance, and ergonomy, for example. And Satoru does a lot of this real, like, robots in the wild deployment, where you have this really physical, you have to think about this physical behavior of people towards robots and vice versa. And I think these are all like very at the core of HRI research. But for a conference like this, RSS, it feels like we are much more used to, or more comfortable in talking about, I don't know, SLAM and grasping and motion planning. It feels like there's always some pointers which you can follow and get what you want. But in terms of HRI, I think it's very hard. I don't know, for some reason, I feel like, although it's a very important problem in service robotics, it's not being addressed, or I don't know, it's not being educated. People are not being educated, or I don't know. Maybe RSS is not the conference. I'm not very aware of the other conference that really do HRI, but it feels like to bridge this HRI and robotics gap, which is, I think, essential for service robots, we are lacking quite a lot, I feel.
My guess is that just the history of RSS and how it was founded is why it's so SLAM heavy. Which is fine, right? Like everyone kind of knows there's going to be equations and you have to have that if your paper is going to get accepted. And that's just different from the kinds of papers that we tend to publish in HRI. So if you're looking for those papers, the ACM IEEE conference on human-robot interaction is probably where most of the action is at. These days, there's a lot more getting published at CHI, the ACM Human Factors and Computing Systems conference is another place where there's a lot of this kind of work if you're looking for that. And I think it's the folks who do more, an algorithmic contribution is something that you're more likely to see at RSS, as opposed to, a controlled experiment where you look at how to get children to stop bullying your robot, right? Both are valuable. It's just that we kind of, like for me as someone who's writing these papers, like I'm not going to try to submit an empirical paper to RSS because the reviewing committees don't really know what to do with it, right? And I've served on the reviewing committee for RSS in order to try to help bring in more of that in to the conference, but I think it's still like slowly increasing, but we're not quite there yet.
And is there also like a gap? How do you see this gap in these kinds of research for service robots? Like what academia does, and it feels like, I was just looking at the video that Serena gave to me, and I found it interesting that she shows this experiment where you have this interface to teleoperate a robot that was actually engineered to make the operation more efficient and easier. And there's also this interface with just like the Kinova, like I think a standard
the joystick
control. The joystick, yeah. And although people are worse with the joystick, they still prefer the joystick, right? It's like
yeah, because the problem is that sorry, Just to comment on this work, we recruited 40 participants from outside the lab, like random people, without background in robots or without, and they were not lab student also. And so these were really people that were like projecting in the use of these robots, and it's another way of reasoning. We are too much used to have students in the lab that evaluate our system, and they have, even if they are not the students directly involved in the platform, then they know a little bit, they're immersed in a certain environment, so they have a prior. And it's not the same as the people, like real people from outside or real end users. And I discovered, trying to apply our systems in the real world, I discovered that we have a big problem, which is interfaces. Ranging from like hardware interfaces to software interfaces to explainable interfaces, where people can really figure out what is going on. Because sometimes they really don't have a clue about what the robot is doing and what's inside the robot, like how the control works and so on. Whereas students have an insight of that. So they already have the insight. And this really makes a difference. So that's why, I mean, a portion of what we do is also focused on questions more related to interfaces and usability, how to make it work and applicable to other people.
Yeah, agreed.
We would break. Oh, sorry, please go on.
No, go
but
ahead.
This is not work with equation. This is the problem. It doesn't sell in papers.
Yeah, humans are very noisy creatures. We're noisier than robots. And so at least most of my, robotics friends are like, you just deal with the people. They're such a pain in the butt, right? And if we could simulate them, we would. But if we could simulate them, then we would have solved all of psychology too. We're not there yet.
I think this is exactly why. So the thing the thing you were saying about the fact that it's better for the robot in the mold to have the human operator taking decision, because the behavior that is facing in the real world is so complicated. I mean, I see no way to have it fully autonomous without making errors or without making something that could lead to a rejection, for example, of the use of the robot. Because if people then say, okay, it's weird, it doesn't work, okay, we don't use it. And this for us is a failure at the end. It's the ultimate failure.
Exactly, the human factor is very noisy. In my cases, we put a robot in the shopping mall, some stuff, and then evaluated the effect of the robot services. So the very rated one is a robot try to approach to the people who is using the smartphone while walking, and the robot said, stop, do it. Then, so what kind of design of the behavior the people stops such a kind of things? So this is an evaluation. So in this case, we put the robots and wait the people who have no smartphone. If find out, so the automatically detection is completely difficult. Then we use a human operator, just select the target, then robot after that automatically worked. Then we counted the number of the people and number of the people who stopped the smartphone and compared designing. So this is some kind of the evaluation of the human factor and the design of the behavior. So, and it's sometimes we tested in some couple of things that incomplete part isn't including. So we keep some kind of the safety system that the human operator doesn't harm the actual visitors or some stuff. So such a kind of full set of the experiment should be very, very tough work sometimes. And it's necessary to the actual people, actual environment, actual situation. So this is the one difficult point for the evaluation of that.
Yeah, our sample sizes tend to be small because of that. It's just a pain in the butt to get the robots to work robustly enough to run an experiment and then get people who are of the right population of people that we care about, right? A lot of people talk about, we would love to do caregiving for older adults. That means you better go out and recruit older adults, right? Don't just say that it's going to work for them too, because they're going to respond in their own way. And that's important for human-centered research.
I think so. It's the contents of the human-robot interaction, of course, depends on the robot ability. How can I say? For example, case of the picking. So how there are, if the human wants to ask the robot and someone try to pick someone, but there are many ways to make the commands. Ambiguity or difficulty. Actually, I know the preferred network one published one paper about such an interaction the robot can picking. So maybe SRAM or such kind of the technology, of course, directly related to the work on the human-robot interactions. So yeah, that kind of connection is very important.
So just to chime in, as everyone said, creating kind of the right kind of tests and running evaluations with robots for human-robot interaction is really tricky. And for that, we established a workshop series at HRI that looks at this. So this is together with the National Institute for Standards and Technology, so NIST. So the idea is to come up with at least rules of thumb or best practices for performing these experiments and trying to foster exactly this kind of the ability to reproduce the results, especially when there are humans present. Because I mean, as Leila already said, kind of depending on the population you have, you may get completely different results. So we tried to establish a workshop series so that already happened 2 times, and we'll hopefully do it HRI 2021 again. It's a very big problem.
I agree, because one problem we have is when you do the experiments like in realistic conditions, you're not in the lab, so you don't have the access and the availability of all the equipment that you usually have to have ground truth measurement on what is going on. So if you're like in the mall, like in the case of the robot in the mall, I mean, you can count events, you can count behaviors, but probably you cannot access everything that is happening, like the precise location of all the people and without occlusions or whatever that allows you to reconstruct exactly what is working. So I completely agree. And because one point of so to add more on that, I think it's very important that all the methods that people use to evaluate real experiments, like questionnaires, are published together with the papers as well, as the same as in the code. Because a lot of times I read papers where they say, okay, we evaluate this and this and this, like some constructs or some usability metrics, but without providing the access to the most of the time it's like questionnaires or the question that they ask in the interviews.
Yeah,
and this
that makes
would
it
allow to
repeatable.
have this is like to enforce reproducibility.
Yes, Leila, do you wanna?
I totally agree. I mean, you can't make reproducible research. You can't really call it science unless you reveal your methods, right? So someone else could redo it too and see if it works for them. Also, I mean, I wish we could have human simulators, but we really don't know how people are going to respond in a lot of situations. And so there's many aspects of human interaction and behavior that we can't simulate because we don't even know what we would do, right? And lots of times you'll interview someone and they'll say like, oh yeah, that'd be fine. I would love a robot in my home. And then you stick a robot in their home and they do not behave the same way that they said they would, right? And that's interesting and important to understand. So I think the behaviors matter just as much as the self-reported perceptions. And that gives us new insights, right, for designing robots. It's just frustrating that we're not very predictable.
Yes. Okay, I think we are about to run out of time. Yeah, so I think maybe some people have to jump into other workshops. That's why I don't want to hold here more than this. So I think, yeah, it was very interesting discussion. I thank everyone again for being here and all the organizers also. Yeah, and so from now, I think let's finish here this panel. right? I think there were a lot of lessons, and I think it'll take some time for me to digest all of them. I'll try to write something in the website after. And from now, I think people who are, you're free to leave if you want, but those who are still want to stay for let's say 1 hour from now, we can just have this free session, and we're free to talk about any topic. But people who have other things to do, please feel free to leave. So let me.
Thanks for organizing. It's good to have these discussions.
Yeah, thank you.
Completely agree.
Yeah,
thank
welcome.
you so much for having this. This is amazing. It's good.
Thank you. Thank you.
Yeah.
Thank you.
Yeah, thank you very much.
Absolutely.
Good to see everyone.
Thank you very much.
Thank you.
Maybe next time it'll be in person.
Yes, hopefully.
Though a shout out to the virtual thing, because it's, as was the comment made, it helps get a wider audience potentially.
Mm.
But I agree, in person would be awesome.
Yes.